Right, hello A-level chemists. I'm just going to give you a little run through a lesson that I give my AS students towards the end of year 12, and it's like a guide through organic chemistry in terms of year 12 organic chemistry, and I describe it as like a pathway. How do you make all of the different organic chemicals that you'll come across in year 12 from one very simple starting point. So I'm going to try not to waffle too much, and I'm going to dive straight in. Okay, so the first thing to say is that organic chemicals often contain carbons and hydrogens. So here is an alkane, the stuff that the sort of molecule you looked at in GCSE quite a lot when you talked about fractional distillation. And we're going to consider this sort of molecule our initial building block in organic chemistry for year 12. Now the thing about this alkane is that it's chemically quite boring. It doesn't do very much, and one of the main reasons for this is because the carbon-hydrogen bonds are non-polar. So a lot of A-level chemistry is to do with your understanding of electronegativity, and carbon and hydrogen have got very similar electronegativity, so each of these bonds are relatively non-polar. So we say that alkanes are non-polar molecules because the carbon and hydrogen bonds don't really have any sort of significant dipole. You can't write delta negative and delta positive on these. So this means that other reactants are not really particularly interested in this molecule. You put an OH minus next to this molecule and it's just going to look at that molecule and it's going to go, hey, I'm not really interested. Why would I be interested in this? You put an HBr around this molecule, again it's going to go, right, there's nothing for me here. So alkanes are chemically fairly unreactive. I mean, you can set fire to them, but because they don't have a polar bond, not a lot happens. So I'm going to build up A-level chemistry from first principles in terms of A-level organic chemistry, from first principles. And we're going to do it in this sort of way. We're going to take an alkane and we're going to make it more interesting. We're going to introduce a polar bond into that alkane. And what you'll see that once we've introduced a polar bond into the alkane, it can start to do some very interesting things. So, you ready? Well, we'll start now. That was an awkward pause, wasn't it? Right then, so the first thing that I recommend that you try and get your head around is how do you make an alkane more interesting. And what we do for that is we do a type of reaction called free radical substitution. And what free radical substitution does, now it's really important that you know what it does and why you're studying it. It introduces polarity. It introduces a CCl, a delta positive, delta minus, so a polar bond. So once you've got this polar bond into a molecule, you can do lots of interesting things. So what you do here, you take a molecule like this, an alkane, remember I said, chemically boring, non-polar molecule, nothing's interested in it, and then you take some Cl2, some chlorine, you react it with a little bit of UV light, some magic happens, and you end up with a chloroalkane, a halogenoalkane, which has now got this very interesting delta plus, delta minus. Now, I'm not going to go into free radical substitution, the mechanism, because, plus HCl, because that's not the purpose of this video. You need to know for free radical substitution, you've got to know that mechanism. Your teacher, whatever school you're at, will have told you that you have to initiate, you have to propagate, where there's going to be 2 arrows. Initiate is 1 arrow, propagate is 2 arrows, and then terminate, which is 1 arrow. Now, if there's a desire for me to go through each of these individual mechanisms, I can do that, but this is just the guidebook. Alright, so what we've got then, free radical substitution, its purpose, and this is the important bit, its purpose is to take alkanes and react them with a halogen to make a haloalkane. One second. Sorry, that was just my daughter shouting from downstairs. You make a haloalkane. That is the purpose of free radical substitution. So what I'm going to do, just on a separate page now, I'm going to start collecting this. So what you've got an alkane. Could be any alkane. And what we've turned it into using free radical substitution is we've turned it into something a lot more interesting, a haloalkane. And I'm just going to represent it like that. So free radical substitution, if you're asked, it introduced halogens into molecules so that you get polar bonds. That's a really good way of thinking about it. Okay, you've got to learn what free radical substitution is, unless you want me to go through it. Alright, next step then. What do you do now you've got a haloalkane? And haloalkanes now are really, really interesting molecules because of this polar bond. Alright, and you often ask that in exams. It's the polar bond that makes haloalkanes interesting. Alright, so what can you do now you've got a haloalkane? In fact, I'm just going to go onto a separate piece of paper and I'm going to talk you through the possible routes. And this is the introduction of one of my diagrams. Okay, so I like to draw this diagram. I draw a box in the middle. And in here I'll just draw a generic haloalkane. 1, 2, 3, that's chloropropane, or sorry, 1-chloropropane. Could be anything in there. It's a haloalkane. The point is it's got a polar bond. And there's a number of things that you can do with a haloalkane. In fact, not just a number, the number that you need to know is there is 1, 2, 3, I'm drawing 2 arrows there, 4. This diagram has real purpose and I didn't mistakenly put 2 arrows up here. So there are actually, at AS Chemistry, there are 4 things that you can do with a haloalkane. It's worth remembering that. There are 4 things that you can do with a haloalkane. I could now ask you, how did we make that haloalkane again? And you go, free radical substitution. So you know where this thing came from. It comes from free radical substitution. Little story. We get crude oil from the ground, we get alkanes, we then react with chlorine in the presence of UV light and we make a haloalkane. How many things can you do with a haloalkane? 4. Alright, that's where we're at. So the things that you can do with a haloalkane, 3 of these things are different to the 4th, so I like to draw a little line down here. This one's different, so this diagram is telling me there are 4 things you can do to a haloalkane, but one of them is different to these 3. These 3 are all grouped together. This one is grouped separately. This one's getting me interested as well, the 2 arrows one. Alright, everything on this side is of a certain class of reaction. I'm going to write down the reactants for you. OH minus, CN minus, excess NH3, excess ammonia. Each of these little reactants has got a little lone pair on. That's got a lone pair on the carbon, that's got a lone pair on the oxygen, that's got a lone pair on the nitrogen. No room, I'll just draw it up there. This is done under warm aqueous conditions. This is done ethanolic. So that just means dissolved in ethanol. Don't write ethanoic, that's not correct. Ethanolic, ethanolic. And this is done typically ethanolic as well. The reason we do things in ethanol, again I haven't got time to go into everything, but we don't want to introduce water here as well because that can confuse matters. So do you recognise what these 3 things are? They've all got a lone pair. They can all act as lone pair donors. That's right, they are nucleophiles. So all of these 3 are nucleophiles. That's lone pair donor. So the things that they can do is they can do nucleophilic substitution. This diagram tells me that there are 3 different nucleophilic substitution mechanisms that you need to know. So if you've got a haloalkane, you can react it with OH minus, CN minus or NH3 in nucleophilic substitution. Alright, there are 3, that's it, no more. So the OH minus comes in nucleophilic substitution. Well, I'll just draw it on here. The lone pair attacks that delta positive carbon and this comes and the chloride drops off. So what we're going to do, I'm just going to go boom, boom, boom. Instead of a Cl here, I'll draw an OH. Boom, boom, boom. Instead of a Cl, I'll draw a Cn. Sometimes drawing a C triple bond then. And here it goes boom, boom, boom. And instead of a Cl, I'll draw an NH2. not an NH3. The two arrows here remind you that there are two steps to this mechanism. That is the hardest mechanism out of these three. Alright. Over this side there is another thing that you can do to a haloalkane, and that other thing is you can react with OH minus under hot ethanolic conditions. Don't know what I was going to, or reflux, we often say. Reflux means to boil and boil and boil without evaporation. Alright, hot ethanolic and reflux. The E of ethanolic gives us a really big clue that this is a different type of mechanism, and it is in fact elimination. The OH minus does not act as a nucleophile here. You have been taught by your teachers that the OH minus acts as a base. Alright? A base is something that picks up H pluses. So when something acts as a base, OH minus acts as a base, it reacts with H plus to make H2O. Alright, bases react with acids, don't they? So bases react with acids to make water. Alright. So what happens here is when the OH minus reacts as a base, this Cl from this haloalkane and a neighbouring H off here will be eliminated, and you will end up with boom boom double bond. You will make an alkene. Alright, so these are the things that you can do to a haloalkane. You can turn them into alcohol. You can turn them into nitrile, very much an A2 molecule, that, and you can turn it into amines. Again, you do a lot more about amines next year in year 13. Alright, and you can turn them into alkenes. So we've gone from, let me go back to that little diagram I was sketching up here. Right, you can take an alkane from crude oil. You can do free radical substitution in the presence of UV light to make a haloalkane. That haloalkane can be turned into 1, 2, 3, 4 different things. 3 of them by nucleophilic substitution, 1 of them by elimination. What do you make by elimination? I remember that. You make an alkene. What do you make here? You make the alcohol down here because that's OH minus. What do you do up here with NH3? Well, you make NH2. What you do over here? Well, you can make a nitrile. Do you notice on this diagram that we've got OH minus here and OH minus here? Alright, OH minus in 2 different situations. The examiner of course is going to ask you about adding OH minus, and they're of course going to try and catch you out. The key is, the simple way to do it, if it's OH minus and they mention with ethanol, OH minus with ethanol, that's elimination. You're going to make an alkene. OH minus warm or aqueous, you're going to make an alcohol. Alright, so now we're on to the next stage then. From this molecule we can go to lots of different places. From this diagram, sorry. Nitriles you look at in year 13 can go on to make amines. Amines can go on to make amides and lots of interesting molecules. Again, year 13. Alcohols though, we go into a lot more detail in year 12. Alkenes is where our next stop is now on this little journey. So imagine then we've got an alkane. We can turn an alkane into a haloalkane. It's now chemically interesting. It's got a polar bond, so nucleophiles are interested in that delta positive carbon, and we can turn alkanes into alkenes. Alkenes, interesting molecule, next type of reaction. Okay, so what can we do with alkenes? Right, alkenes. So I draw a little box in the middle. Alkenes, I'm just going to draw an alkene on here. Alkenes can react in 3 ways that we're going to look at in AS. Alkenes can react with HBr, alkenes can react with Br2, alkenes can react with H2SO4. Alright. You react an alkene with HBr. So what happens is the H and the Br attach over this double bond. H can go here, Br can go here, or the H can go here and the Br can go here. You have to know little rules about unsymmetrical alkanes, but anyway, you make this Br and H, or you make this H and Br. Little question for you if you want to pause the video. Which one of those is most likely to form? That one. Alright, again, God, there's so many videos I could make, but I only have a certain amount of time and a certain amount of inclination. So, what happens here is this HBr adds over this double bond. These are electrophilic addition reactions. That's an electrophile, that's an electrophile, that's an electrophile. Electrophiles are lone pair acceptors. That's the only thing you need to write. Electrophile, lone pair acceptor. Nucleophile, lone pair donor. Alright, add Br2, well that's easy. You're going to add a Br and a Br, nice and symmetrically. And down here you're going to add H2SO4, slightly more tricky. You're going to make H there and O, S, double bond O, double bond O, O, H. Alright, God, that's a video in itself, isn't it? That can then go on to make alcohols if you react with water. Alright. So the examiner could ask you, how many things can you do with an alkene? Well, you can turn an alkene into a haloalkane, and you're sort of back to where you were. You can turn an alkene into a haloalkane, which you know you can do 3 things with haloalkanes. Or you can turn a haloalkane into an alcohol. Alright, so let's go back to the overall diagram. In fact, I'm just going to draw it out all from scratch again because it was getting a bit messy. So, what could you do? You could drill some crude oil out of the ground and you could get an alkane. Alright, alkanes, they haven't got any polar bonds, so what do we do with them? Well, we do some free radical substitution. If you do free radical substitution, you make haloalkanes. Haloalkanes can be reacted in 4 different ways. 1, 2, 3, 4. 2 of these ways involve OH-. Alright, one of them involves ethanol. This is different. This is elimination. Elimination of a haloalkane gives you an alkene. In this case, that I've just drawn that one, so it's going to be ethene. All of these are substitutions, so you're going to make OH, Cn, because this is with Cn minus, excess NH3, you're going to make boom, boom, NH2. Alright. You can then take this alkene here, and alkenes can be reacted in 3 ways. HBr, Br2, H2SO4. Alright. HBr will make HBr, which is basically a haloalkane. Br2 will make that, which is basically a haloalkane. And H2SO4, by a couple of steps, will make an alcohol. On this diagram, how many different ways are there to make an alcohol? There's one, and there's another one. So this is what I'm trying to teach you, is like, if somebody says, how can you make an alcohol in A-level chemistry? Or what you could do, you could take an alkane, you could do free radical substitution with chlorine in UV light, and then you can use warm aqueous sodium hydroxide to make an alcohol. Or you can take an alkene and you can react with H2SO4 and then a little bit of water and you make an alcohol. And then someone will go, where do you get your alkene from? Well, you can get your alkene from a halogenoalkane that you've reacted with hot ethanolic OH-. By the way, you can also get alkenes from a second place, which I hope you realise you can get them from cracking as well. This is why you got to turn up to all your chemistry lessons and listen really hard to your chemistry teachers, because there's links all over the place. I'm trying to introduce the idea that chemistry is all linked together. Alright. So, by this stage, we've made alcohols a couple of times. We've done electrophilic addition. We've done nucleophilic substitution. We've done elimination. 1, 2, 3 mechanisms that you need to know, and free radical substitution, a 4th mechanism, doesn't need any curly arrows. So there are 4 mechanisms so far. At this stage, there's a couple of sneaky little mechanisms that come in, alright, that need separate learning. They're very similar to other mechanisms that you've done, but they need some separate learning. These mechanisms are you can take an alkene and you can react an alkene with H2O in the presence of concentrated acid catalyst, and you can make an alcohol. Alright, this is called hydration of alkenes. And you can also take an alcohol and react it with concentrated, I think it's sulfuric acid this way, phosphoric acid that way. You can react it with concentrated acid catalyst, and you can turn it back into an alkene and water, which is known as dehydration. So there are two other mechanisms here. One, adding water, hydration. I'm telling you what, I could do with some hydration now. Not joking, I am sweating cobs. Dehydration is that way. These are two other mechanisms that you need to know. Hydration and dehydration. And these interchange alkenes to alcohols and alcohols back to alkenes. Now you do know another alkene to alcohol mechanism. You do. It's up here. You can use H2SO4. So this is separate to that. But this is hydration and dehydration. Two other mechanisms that you need to know. There's a lot of noise going on downstairs. We're playing in the paddling pool. Me kids. Right then. So 20 minutes in. Probably about time to sort of draw this to a close now. The very final thing then is, by the end of your organic chemistry, you do a really big topic on alcohols. Remember, we've made alcohols in a few different ways. Let me remind you of the ways that we've made alcohols. So here's that little diagram again. Where have we made alcohols? We've made alcohols here. We made alcohols here. We made alcohols here, which is hydration. So how can you make alcohols? You can take a haloalkane, OH- aqueous. You can take an alkene, concentrated H2SO4 followed by water. Or you can take an alkene, concentrated phosphoric acid, and some water. Alright, 3 different ways to make alcohols. So then, we have a whole separate video here dedicated to alcohols, which introduces this lovely diagram. Primary alcohols, secondary alcohols, tertiary alcohols. Tertiary alcohols, this diagram tells me there's not a lot you can do with that. Secondary alcohols can be turned into ketones. Primary alcohols can be turned into aldehydes, and then onwards into carboxylic acids. There's a little teaser if somebody wants to know a little bit about this diagram. Let me just add all the interesting stuff to it. Alright, what could I write on here? Distill, reflux, there's loads of stuff you can write on here. So alcohols can be turned into carboxylic acids, aldehydes and ketones. It's probably where you just about, if I'm recording this in summer, you're about up to this point in your learning. Alright, so let me take you back to the start, just as a little summary. AQA AS mechanisms. This is a pathway starting at alkanes. If you start at alkanes, you can make a whole load of different molecules. Alright, a whole load of different molecules. But let me remind you then, alkanes are boring because they're non-polar. Nucleophiles with their lone pair will not be interested in any of these atoms. HBRs with their delta positive negatives and their delta positives will not be interested in any of those atoms. So the first stage on this pathway is to really make an alkane more interesting by adding a Cl-. When you add a Cl, you make this polar bond. There we go, this polar bond here. Once you've got a polar bond, goodness me, you can get to work and you can do a lot of chemistry on it. Once you've got a polar bond, you have this diagram. You can make amines, nitriles, alcohols, alkenes. Alkenes can be turned into all sorts of interesting things. There's my alkene diagram gone with rustling paper here. There's my alkene diagram. You can make it into 1, 2, 3 different things. You can also hydrate and dehydrate. Alright. I haven't even spoken about what else you can do with alkenes. You can turn them into polymers. Alright. God, chemistry is complicated, isn't it? But hopefully this is giving you a little bit of a pathway through. And then alcohols, which we've made in a number of different ways. Here's the 3 ways that you can make alcohols that you know of. You can then do some really cool stuff with them. You can turn them into carboxylic acids, aldehydes, ketones. Lovely stuff. Alright. Scratching the surface there, aren't we? Because most people who go on YouTube to look up videos about AS mechanisms probably just haven't learnt the mechanisms. This requires you to know the mechanisms, but it just gives you a little pathway through how one molecule can be turned into another. Watch this video twice, you know, listen to me talking through it a couple of times, see if you can get your head around it. But I haven't taught you in this mechanism. What I haven't taught you here, I haven't taught you how to draw a nucleophilic substitution mechanism. I haven't taught you how to draw an elimination mechanism or an electrophilic addition mechanism. I haven't taught you how to do a hydration mechanism or a dehydration mechanism. I've not taught you any of that. I've just shown you how they all link together. Alright. I'm not going to watch this video back. I'm just going to put it out there and see what happens. Alright. Thanks for watching. Yeah, done.